you.
Thank you.
Oh, thank you. I got chicken,
Uh-oh. We went over that.
I want to see how you guys came up with that number. How'd you get 866 or what did you get? How did you get that?
I put down 600.
I
I put down less than 600.
I figured it to be 900 for the kick out and 600 for the kick in.
Yeah, kick in, I got less than 600.
We got 909, I don't know how I got 909, but.
All I did was I used a surface area of a third of a square inch on the ball, and the piston has got a surface area of 1 inch, and I just plugged in numbers to get to the balance point. And let's see if I can find that here. Generically to kind of show you. You're lying. Okay, is everybody here? I graded your homework assignment, but I'll give you credit for one of the questions. The first one, if you can explain to me how you got the numbers you got. Okay.
How'd you get 900?
Okay, well, I just did it by trial and error. I put 900 PSI into the circuit and I saw what the response would be. So for example, if the pump is pushing out fluid and the accumulator and the pressure line are seeing 900 PSI, that means that there's 900 pounds of force that's being generated. So you got 900 PSI pushing in a 1 square inch piston at 900 pounds of force pushing up, okay? So, okay, so you got that. But what's pushing down in a couple of cases, you've got the spring, you've got 600 pound forces pushing down. And then if the surface area of the ball that's also aiding in holding the relief or the relief valve seat or the aluminum valve seated is 1/3 of a square inch. 600 plus 300 is a total of 900. So that's kind of like the tipping point. You get to 900 PSI and then all of a sudden at 901, the ball is lifted off of the seat. And then at that point, the only thing that is keeping the piston elevated is really the pressure that's beneath the piston against a 600-pound spring. And then the pressure would have to recede to about 600 PSI before the ball recedes again. So that's what I kind of came up with. I figured that the kickout was going to be at 900 PSI, and then, okay, you've got 300 pounds that's working downward on the ball. That's 1/3 of square inch surface area over 900 pounds. Then you've got a force of 600 pounds pushing down by the spring. Okay, so the total sum together is 900 pounds. And when it's in the kickout position, the only thing that's holding the piston up is just the fluid under pressure. So as soon as the pressure diminishes to 900 or 600 PSI, the ball will recede. How did you guys come up with the other value that you came up with?
I kept it with the figures. Other than the figures that were changed on the question,
Yeah.
I kept the same 800 that's in figure 83. That's how I got 866. Because 1/3 of 800 was 266.
1/3 of 800, 266. Does it balance at that point?
Or I don't know about balance. That's how I got that number.
Okay.
But I kept the same system pressure that's in figure 83, which was 800, and that's where I got 1/3 of 800 was 266.
Okay.
So the only thing I had changed was the 1/3 from the quarter that it was for the surface area for the ball. To
Oh.
the 1/3.
Okay, I'll give everybody credit for that question, but do you see how I kind of calculated it? You have to have a balance of forces in order to override the point where the ball comes off of its seat. So I just used 900 PSI arbitrarily, but if you use any value smaller than that, the ball still stays on its seat, so it's technically still kicked in. You know, that's how I kind of figured it.
Because other than the ball, I kept all the figures the same for the system pressure. That was in the figure. Because in figure 83, it says 800 for system pressure.
Okay.
So I just kept that same
Yeah,
pressure.
so we,
I get it. I'll give you credit for it. If you kept the pressure at 800, I guess I understand how you figured it. Okay. All right. Okay, tonight anyway, we're going to talk about schematics. We'll also talk a little bit about what else? Testing and support equipment. So a couple of different topics tonight for discussion. Okay. We've spent a lot of time talking about components, and we spent a little bit of time trying to build those components into systems or circuits. And just kind of a review. The Fluid Power book still uses pictorials for a lot of their schematic illustrations, and really today it's not too common to see that for modern hydraulics. So if you look on page 216 of the Merrill Fluid Power book, you'll see a picture that kind of looks like this. They've got what's considered to be the power section of hydraulics. They've got the reservoir, pumps, and pressure controlling devices on the left-hand side of the circuit. Later on, they developed a circuit showing directional control and an actuation. So they're showing what they're using in the circuit. Just what they consider to be the power section of the hydraulic system. So we've got a pressurized reservoir, and I know that because it looks like they've got a venturi T that's plumbed into the circuit. So they're using return system fluid that comes back into the reservoir to pull air through the throat of the venturi, and in that way they pressurize the reservoir. They also got a dehumidifier of some type attached to the line that draws air into the throat of the venturi, so hopefully that somewhat keeps the air somewhat free of moisture. Usual sight gauge, looks like they don't have remote reading for indication of volume in the reservoir. They do have a standpipe in the reservoir, and we can kind of figure out where the main system is and what the auxiliary system is. The main system is kind of plumbed so that we receive fluid from a standpipe and it goes directly into the circuit. And then if we've got an auxiliary pump, usually that's attached to the very bottom of the reservoir. So that's why they did that here. They just got a very small opening down at the bottom that draws fluid from the very bottom. rather than use a hand pump for emergency use, they consider this to be an auxiliary pump, and it's electrically powered from a circuit breaker in a bus. It delivers flow into the pressure manifold, and then what it does is eventually it'll cause this selective relief valve to be lifted up when the pump is in use, and it allows ultimately, I think, that pressure to be made available into the pressure manifold. And that's about really its only function. I don't think it's able to deliver flow any other place other than into the pressure manifold. The normal power pumps that they have in the circuit, they're both, they're kind of strange. They're using variable displacement pumps for 2 of the pumps, and the other 2 pumps are constant displacement. And you can see that 2 of the pumps, in this case the right pumps, they don't channel off into the pressure regulator, so we can kind of infer from that that they're internally controlled for volume based on pressure. And then the other pumps that they have in the circuit, they channel into a couple of check valves that goes into a pressure regulator, so those pumps are going to be constant displacement. Anything else, they've got solenoid operated shutoff valves. In the event that we intentionally want to starve the pumps of hydraulic fluid, we can by shutting off the flow. And what else do we have? Oh, the selective relief valve. This is kind of like a priority valve in a way. The idea is the valve is normally held open by system pressure. And what it does is it makes this brake accumulator exposed to the entire hydraulic circuit. However, if hydraulic pressure in the main manifold should drop for any reason, this priority valve or selective relief valve will close, and it makes the accumulator exposed only to the brake system. They consider that to have somewhat of a priority in nature. So rather than the pressure should drop off, they want to preserve whatever pressure is remaining in the brake accumulator specifically for that use. Anything else? Indication of pressure. They've got a gauge that's mounted in the pressure manifold, or at least a transmitter, for remote indication of pressure in the aircraft. Like I mentioned earlier, for many aircraft, it's advantageous to have remote reading. Rather than have a direct reading gauge where you have fluid pressure in the cockpit, this is a much simpler method of display of pressure. It's also a lot safer. All you have in the cockpit is wiring and the gauge itself, so you don't have exposure of high pressure fluid in the cockpit. So if you develop a leak, kind of no harm, no foul as far as safety is concerned. You've got a direct reading gauge on the gas side of the accumulator. So when you empty the accumulator of fluid by releasing the fluid from the top of the accumulator above the bladder, you're able to visually detect what the pressure of gas is in the accumulator for the precharge. And once the pressure in the hydraulic system exceeds the gas, or balances the gas pressure, that same gauge could be used to indicate what system fluid pressure would be. The protective devices in the circuit, they've got a pressure regulator. This establishes kick in and kick out of the 2 of the pumps that are used, or unloading of 2 of the pumps that we have in the circuit. A secondary device for protection would be the relief valve. The relief valve doesn't unload the pump, but it's set to a higher value for its kick out, so that in the event that the pressure is skyrocketing too high, the valve opens in order to divert flow back to the reservoir. They also have kind of an unusual valve that's in the circuit. I've never seen it used in actual aircraft. I'm kind of wondering why they did this, but they have what they call a bypass valve that's energized by a separate valve called a bypass control valve spool. And when this valve is energized electrically, what it does is it takes hydraulic fluid under pressure and takes the pressure regulator out of the circuit completely, so that I guess you don't even have any feed of fluid flow going directly to the pressure regulator to keep it from the pumps through the regulator. Kind of allied with this kind of idea as well, if you look at some military aircraft where they have a landing gear system that's hydraulically powered, once the gear is retracted, the particular setting for up, it cancels hydraulic pressure that's retained in the circuit for holding the gear up. That's done as a safety feature for some military aircraft, so that in the event that the aircraft is struck with a projectile, you're not going to be spewing hydraulic fluid. So it provides a dump of hydraulic fluid back to return once the gear is locked in the up position. I don't know why they did it in this particular circuit by moving pressure from the regulator, but they did. Anything else, the selector valves are kind of strange. They use a combination of open center and closed center selector valves in the circuit for operation of the equipment that's downstream. But this is what we have, at least for the power side of the circuit. Oh, also notice too, check valves. For isolation of inoperative pump via maybe a broken shear shaft, they use check valves to prevent motoring of the inoperative pump. So that's kind of common on many of the multiple pump designs that feed into a common manifold for discharge. Landing gear circuit, it uses hydraulic pressure to keep the gear up with up latches, ultimately latching the gear in the up position. And then once the gear is unlatched for down, the main gear anyway, hydraulic pressure is really not too important. They use the weight of the gear to lower the gear down as a part of the load. And then there's integral action or locks that hold the gear in the lock position. But they have single acting actuators that are used in order to lock the main gear up when it's in the stowed or retracted position. And those first have to be unlatched before the gear is allowed to fall and come down. The nose gear, it looks like they use a nose gear up latch actuator that has to be have pressure applied to it before the nose gear can latch and fall down. But the nose gear itself, I think they use pressure for both going up and also retracting it, or extending it. So you might find that the nose gear, because of the way that the geometry that it works, they have to use pressure in order to be able to extend the gear against an air load. They have an emergency feature for gear down. They use a separate valve that they push over a piloted valve spool in order to divert flow for emergency extension of the gear. And anything else? Not really. Again, kind of a strange selector valve that makes all of it kind of happen. I think we talked about this too. Some brake systems in aircraft have, for power brakes anyway, we use the multiplication of force in order to be able to stop heavy loads or at least create the friction necessary to stop big aircraft. This would be part of a dependent brake system. And dependent means that we use main system hydraulic fluid that is being metered in order to control brake friction. The way that they do it is by a valve that they call a power brake control valve. In the landing gear class, I know Lyle has got a cutaway or two of these devices. They're really spool-operated valves that are work against an internal spring, and it gives you a sense of feel, and at the same time allows you to meter a certain amount of brake pressure, system pressure, to control the brakes. It's a little bit different than a master cylinder. A master cylinder, what you're doing is you're confining fluid that's going to the brake itself, but this device, it's actually metering brake system pressure by a spool-type valve. What do they use for emergency function? In this case, for this aircraft anyway, they've got a separate system that applies gas that's trapped in a vessel in order to be able to apply brake pressure for emergency means. And this would be a pneumatic system. When the pedal is depressed, in this case, the air pressure is allowed to be metered as well into the brake via shuttle valve. Shuttle valve is pushed over, it isolates the hydraulic port, and then provides for application of brakes. With a lot of pneumatic systems, there's no, well, most pneumatic systems for emergency, there's no recovery of air. So once you expend the air that's inside of the cylinder or the flask, that's kind of the end of the hunt. But that's okay. There's usually, in many of the systems, there's more than enough air held in retention to allow for multiple applications of the brake. Boeing commonly uses this in a way for emergency brakes on the aircraft. Boeing is kind of strange too. They don't generally direct air under pressure to the brakes for emergency purposes. They have a standpipe assembly, or actually they call it a stand tube. And what they do is they push hydraulic fluid under air pressure to the brakes. So rather than use air pressure directly, they push a quantity of hydraulic fluid that's held in reserve in order to power for emergency brakes. The system has got a hydraulic fuse in it, and I think you already know what the purpose of that is. In the event that we have a leak in our brake system, Well, we don't want to expend all of the system fluid from other subsystems through that leak. So the hydraulic fluid usually works on quantity or velocity. And if a certain quantity is expended past the fuse, that's pretty indicative of a leak. So the fuse shuts off at that point. And then from that point on, you'd be using emergency brakes in order to provide for braking force. Okay. Nose wheel steering. This is kind of a simplified schematic, but the actual metering valve is part of a power control unit attached to the actuator. And it has a follow-up circuit in it, and again, it kind of neutralizes the motion of the actuator as the nose wheel is steered. In large commercial aircraft, the method of steering the nose gear is by a tiller. So if you look in the pilot's compartment or on the flight deck, you find what simulates a wheel or a steering wheel, and that's a tiller mechanism. The tiller is attached really to the control that this metering valve is directing fluid with. So when you're making a motion with the tiller control, you're pulling on these cable assemblies which pull this metering valve in order to meter fluid into the nose wheel steering actuator. Many of the nose gear steering actuators, if there's only one of them, will be a balanced type. And again, we've got equal surface area on both sides of the piston so that we have equal amounts of force being delivered to the nose wheel in order to steer it. Some nose wheel steering circuits, though, use two actuators. In that case, you won't necessarily find balanced actuators for that type of usage, but this one does. They've got an oleo actuated shutoff valve. That valve is used to prevent steering the nose wheel while the gear is retracted. So it provides a shutoff automatically as soon as the gear retracts and stowed so that there's no fluid being directed to the metering circuit for nose gear steering. Cargo loading door schematic. This one, like in a lot of transport aircraft, they have to latch a heavy door that can be used as a cargo loading area for the aircraft in the up position, keep it stowed, and they have to be able to lower it down. They use sequencing in this type of system. They'll have latch actuators that are have to be unlatched first before the door is allowed to open. And they do that with this type of actuator. So they get a lock actuator here. And it's sequenced via sequence valves. So it's a mechanically tripped valve in order to, once the door or once the latch is kind of fallen free, then in fact the door is allowed to open. And they'll be repositioned to an alternate position in order to be able to close the door back up. The door actuator free falls open, just like some landing gear. So they use the weight of the door in order to be able to move the actuator and displace fluid out of the actuator back to the reservoir. But obviously, in order to raise the door back up again and close it, they have to direct hydraulic pressure to it in order to get it to close. For door opening, let's kind of take a look here and see how it opens. So you have hydraulic pressure that's available through the circuit through a selector valve. That selector valve ports hydraulic fluid to a flow equalizer, and then it distributes that hydraulic flow equally to both of the latch actuators that have to be able to move ultimately so that the door can open. At some point, what will happen is that rod will push on the selector or on the sequence valve, and then at that time you'll be able to get the door to eventually fall open. Something kind of interesting too. As the door is going to the open position, and here's the actuator for it, the fluid that is escaping out of the actuator has to go through a orifice check valve. And again, we don't want the door to open rapidly. We just want to open it kind of slowly. So as soon as this latch actuator has been opened, it provides for just a limited amount of flow through that orifice check valve that can go back to the reservoir so that the door opens rather slowly. And then the sequence valve will be in the alternate positions in order to be able to close the door back up again. The actuators will bring the door to the closed position, and then ultimately hydraulic pressure is used in order to put the latches back into position as the door finally closes. And it can be powered by means of a hand pump as well, and not too difficult. Mechanical sequencing, again with gear, they do this with sequence valves on a lot of landing gear. It can be plumbed a lot of different ways. The example that I gave in class for plumbing it, there's a lot of different methods for sequencing gear. In some aircraft, they sequence door gear by providing pressure only to the door first, and then as the sequence valve is open, and eventually to the gear for extension. But if we look at how they do it in other aircraft, these systems can be plumbed a little bit differently. Sometimes we can plumb the circuit so that pressure is delivered to both the door actuator and also to the landing gear actuator at the same time. But what they do with the sequence valve is they block the flow of leaving the door actuator. Grumman does that in the S2F aircraft. It works, and again, it works because liquid is incompressible. If you prevent the fluid from leaving the actuator, obviously it's going to go it won't go anywhere. So once the gear finally retracts, then fluid is allowed to leave the door actuator, and then the door closes. So just a different method of kind of doing things. By the way, can sequence valves be timed for operation? Yes or no?
Yes.
Yes. How are they timed? How would you time the let's say, for example, a sequence valve, something was happening a little bit too soon or too late. What would the manufacturer provide for sequence valve timing? They would have a threaded adjustment on whatever touches the pin. So whatever engages or allows that sequence valve the pin to be plunger to be depressed, if the contacting mechanism on it can be changed the distance, that influences the point that the sequence valve opens or closes. Do y'all kind of see that? So, like for example, if the sequence valve is tripping too quickly, sometimes the door is bumping the gear as it's retracting. You might be able to adjust the threaded or the threaded attachment that they have that's touching on the plunger. So it would provide for the gear to fully come up before the door is closed. Do y'all kind of see that? Okay, all right. Wing flap, hydraulic schematic. Some of the flap systems for aircraft are more complex than you think. This one uses a hydraulic motor with a brake. So it prevents the brake prevents the motor from coasting. It positively stops the motor at a certain point once a certain amount of deflection on the flaps has been achieved. But the controlling mechanism is a spool type control valve. And when we pour fluid into it one way, it brings the flap down. When you pour fluid into the other side of it through the spool for the wing control valve, it makes the motor rotate in the opposite direction. And then the brake assembly is used to hold the flap in a fixed position. It also prevents from it coasting to a stop. So, okay. Boosted hydraulic schematic. I think we talked a little bit about boosted flight controls, and really the knowledge base for that is just being able to understand how you're multiplying force by metering the fluid by a small surface area pilot valve into a larger area boosted control unit. If you look at a lot of power control units, PCUs, the spool valve that does the metering is very small in size. So the effective surface area on the pistons might be just a fraction of an inch. However, in comparison, the actual flight control piston or actuator assembly is rather large. So you're getting a multiplication of force against air load by the ratio of those two sizes. And they also talked about, I think when we discussed last week, like a sloppy link. Many of these devices, in order to make the power control unit go to a null position, they use and provide for some slop. They use what's called a sloppy link or a follow-up linkage. What it does is it prevents the actuator from moving too far. So you have to progressively pull on the pilot control valve in order to meter fluid to one side of the actuator or the other in order to get deflection out of the control. I think I've got a little simplified schematic that I forgot to show you last week when we talked about flight controls. And somebody in Australia in a aircraft engineering school did this, and I've tried to contact them. I kind of want to get a copy of what they did. But it's pretty cool. Let's see if I can find it. This guy. So take a look at this. It doesn't show the sloppy link, but it shows the action of the follow-up device that makes the actuator go to a null position. So what you're doing is you're metering hydraulic fluid into the pilot spool. That fluid in turn goes to the actuator that moves the flight control. And as the actuator moves, it forces the pilot valve to go back to a null position and stops the travel of the actuator. So that's the idea behind boosting flight controls. It's more sophisticated than that, but that's the basic idea.
What do those hashes mean on the left-hand side?
It's physically connected. In other words, in many of these hydraulic power control units, the piston is stationary. The actuator moves around it. So this is physically fixed to the airframe itself, and what's moving is the housing that's attached to the actuator, moves back and forth, attached to the flight control.
Is it easier to design it that way?
I think so. You know, I kind of wondered why they did that rather than just try to move the piston with the flight control. But for some strange reason, that's the way that they do it. The housing is attached to the actuator, and the piston is actually stationary. Strange. Right. So anyway, kind of different. Okay, what else? Okay, so that's that. This one, military aircraft, they've got an in-flight refueling probe. It's isolated by means of a priority valve. So if there's enough pressure available, they can have in-flight refueling, but if the pressure should drop off, well, pressure is still retained for operation of the flight controls. They've got a accumulator in the circuit, and okay, so, all right. Oh, we got a blocking piston in this thing. I think I talked about that too. If things go haywire, that's a term my parents used to use. That means not working anymore. Things go haywire. They've got a blocking piston that is pushed down. What it does is it allows for shuttling fluid to either side of the piston cavity. You won't have any boost anymore, but you'll at least be able to prevent slop or in the flight control circuit by manually positioning the flight control. In-flight refueling systems. For military aircraft anyway, they can extend a probe for air refueling. It uses a solenoid selector. This is an ISO schematic of a solenoid selector. So they got two switch positions. They've got three really. They got an off, a retract, and extend. When you put the switch into the extended position, it routes hydraulic fluid into the actuator for extending it. The recovery of hydraulic fluid is made through one of the connections in the solenoid selector that goes back to return. When you put the switch in the retract position, it's a momentary switch in this case, you can retract it again by applying hydraulic pressure to one side of the actuator and recovery of fluid on the other. It looks like it's a three-position type solenoid selector. Center would be off. In one position, you're crossing these two lines together. The other position, you're allowing fluid flow to go completely through it. So I think this thing is alternate action too. They use restrictors, or I should say orifice check valves as well, to control speed. Sometimes, because of the relative sizes of the pistons, they control speed by the use of orifice check valves. So again, to have even speed or control it, they do it that way. In this case, for this aircraft anyway, 5 to 7 seconds for extension, retraction, 9 to 11 seconds. Okay. Strange but true. Some aircraft use hydraulic windshield wipers. These use vane-type windshield wipers, and this is from an S2 aircraft. The speed control is a variable restrictor, so they're using a knob that controls the amount of fluid that's applied to a master unit. You can kind of think of this thing as an automatic selector valve. But what it does is it ports hydraulic fluid into the slave units, which are really the motors, if you want to think of them that way. And it makes a vane sweep from one side to the other. And there's an interconnecting line that they call a balance line. The fluid that's displaced out of one of these on one side of the vane is used to power the vane or the slave unit, the vane on the other side of it. So, and it just makes the windshield wipers go back and forth. Check valves sometimes installed in the circuit in order to prevent back pressure from influencing the operation of these devices. And also, you might find integral relief valves that are installed in the motors. If the blades are restrained for any reason, it prevents the actuator or the motor in this case from damaging itself. So it relieves fluid to prevent that from happening. Another one, this is from a P3 aircraft. This one uses a rack and pinion type of actuator for the hydraulic windshield wipers. They use reduced pressure, of course, but the same method of speed control. It's a variable restrictor that ports hydraulic fluid into the master unit, which in turn controls the speed of the windshield wiper motors. And that's just a picture of the windshield wiper itself. H60 uses that too. I don't know, I haven't found a picture of that, but I know on the early versions of the H60 aircraft, they used hydraulic operation of windshield wipers. Let's now talk a little bit about, maybe about testing equipment for hydraulics. This is somewhat of a complex hose testing unit. I think in the general class, did you not do some hose testing? Did you pressure test a hose?
Yeah.
Yes.
What's the object of the game in pressure testing a hose? You're checking to see if the thing is going to leak at an elevated pressure. So what pressure do you use to check hoses?
It's 1.5 times.
Very good. 1.5 times what? Normal
Normal
system pressure. The standard convention for hose testing or fluid line testing is 1.5 times normal system operating pressure. And I don't know if that was taken out of Part 23 or not, but that's what a lot of people use for testing hoses. You can also use, you can test hoses, you can also test rigid tubing as well. So, but there's different methods of testing. Most of them use hydraulic fluid of what's ever going to be in the circuit as the medium for testing. This one uses a pneumatic pump in order to develop pressure for testing, but more complex than you'll probably find in most shops anyway. We used to, I don't know if they still do they still have the testing rig out in the general area for hose testing?
Yep.
Still out there? Years ago, we had a similar type of device, but we got rid of it. Eventually, it failed, so we had to have a new hose testing unit. For a simple hose testing unit, for a lot of shops, what they do is they just use a hand pump in order to be able to deliver flow. And the hand pump is going to go into a manifold, and usually the manifold's got several sizes of fittings that it can accommodate for whatever hose you got. And then what they have is a shutoff valve. And then past the shutoff valve is they've got, this is going to go back to the reservoir. And then from the reservoir it goes into the hand pump. And then someplace here they'll have a pressure gauge installed. So it's pretty simple. A lot of the hose testing units will have something like a -4, a -6, and a -8 connection for hand fittings. So all you have to do is put the appropriate fitting on the hose and cap it at the end in order to be able to test pressure. To kind of control leakage for a lot of them, they put a catch basin on the bottom of it. So what you do is you bleed the lines of air and then cap off the ends of the tubing or the hose, and then you're able to close the shutoff valve and then use the hand pump in order to develop static pressure in order to be able to check the hose. And again, the standard is usually about 1.5 times system pressure for a minimum of how long? Anybody know?
1 minute.
Not a minute.
30 seconds?
30 seconds. Usually 1.5 times system pressure for a minimum of 30 seconds. So pretty simple. If you want to make this thing easy to operate, what some people have done, and I'll tell you a story, What they'll do is they'll put an accumulator in the circuit that's downstream of the testing manifold. And what it does is it makes the hand pump far easier to operate. If you're just pushing fluid against a closed opening or closure, you're going to have to kind of work really hard in order to get that static pressure up, at least make it somewhat difficult. So they put an accumulator in the circuit. However, there's some danger in doing that. Why is there danger?
We didn't do a good job of doing that.
That's right. If the hose springs a leak, all the fluid that's in that accumulator is going to be vented right out that leak. We used to have a false ceiling just slightly above where the fluorescent lights are in the shop, and there was a big red stain on that piece of ceiling. And that's what happened, you know. So they put an accumulator in the circuit, made the hand pump easier to operate to get the desired pressure. But if you've got a leak, and we did, you'll have a stream of hydraulic fluid that's 20 feet long. Okay, so it hit the ceiling. So again, just told you so. Okay. Let's talk a little bit about jacking aircraft. I got a short video that I'll show you maybe after break about jacking airplanes. We do it in the landing gear class, and I think it's an important thing. I'm generally concerned about a few things around aircraft. One thing that I worry a little bit about is jacking them, because if anything can go wrong, it will. When you jack aircraft, follow the instructions that are in the service manual to its entirety. If they tell you in the service manual that you need a jack stand or a jack pad, you better have one. When you retract the gear, sometimes there's going to be a shift in moment weight as a result of gear retraction. And if you don't have something to counterbalance that shift in moment weight, the aircraft can come off of the pads and you'll punch a hole. Sometimes in the wrong part of the aircraft, you'll punch it right through the skin of the wing and into the fuel cell. So again, I told you so. So read the service manual, because there's a reason why they want you to do that. Many of the tripod jacks are designed for the purpose of getting the aircraft up off the ground for gear retraction checks. So you have to kind of know how to operate them kind of carefully. They've got a central cylinder that supports a screw type of device or ram. And so there's a limited amount of adjustment you can do with the screw in order to make contact with the jack pad of the aircraft. Where you jack is also important as well. There's usually points on the aircraft that will support the weight during jacking that are dedicated jack points. And you have to have the proper jack pad adapter in order to avoid damaging the aircraft. So what they're showing you are the different styles of jack pad adapters that might be used on an aircraft. The hand pump, if it's pump operated or hand operated, it's usually a single acting hand pump. What we do is we transfer the fluid from the reservoir through the pump to the bottom of the ram in order to raise it up. There's usually a safety collar on many of the jacks, and as the jack is being raised up, it's important to follow that safety collar down on the threaded shaft. And there's a reason for that. If the jack should fail during the jacking operation, you want to prevent the collapse of the jack. So that locking collar should be followed down pretty much at the same time that the ram is being extended. There's also an additional lock on top of that locking collar that's used in order to prevent some unauthorized person from loosening that ram lock nut if they try to do it. Be very careful with these type of tripod jacks. The needle valve that's controlling the fluid flow from the reservoir sometimes is not captive. And what that means is if you turn the needle valve out too far, you're going to be spewing hydraulic fluid out of the thing. So you use the needle valve in order to, when you close the needle valve, what you're doing is you're applying the fluid flow from the pump into the tank into the bottom of the jack through the hand pump. When you open the needle valve up, you're returning the fluid flow through back to the reservoir of that pump or the jack. Something else too, they don't bleed themselves quite well either because of the way that the pump or the way that the jack is designed. In some cases, if air is trapped in it, sometimes you have to turn them on their side in order to get the air out of it. And but again, some precautions involving the use of jacks. With a lot of hydraulic devices, sometimes they will bleed themselves of air through normal operation, but with some of the tripod jacks anyway, they don't. You have to turn them on their side in order to bleed them of air. Also too, pay note on how the gear retracts on the aircraft. It's possible as the gear is retracting that the nose or the gear can touch one of the legs on the tripod jack during retraction, and that can also knock the aircraft off of the jack pad. So you have to kind of watch and see how the gear is retracting in order to avoid that from occurring. So prevent it anyway. With just handy jacks that are used or simple jacks that they use for aircraft, those are also pretty simple. The handle that the jack is raised with is also the device that we use to loosen the relief or the valve on it, the needle valve for lowering the ram back down again. So tripod jacks generally for jacking the entire aircraft, 2 or more of them. And then when we use a smaller jack, it's usually for brake and wheel changes on the aircraft too. Also too, if you look to see how they have to jack Cessnas with spring steel gear, they usually have a cuff that goes around the strut of the aircraft landing gear leg. And that allows you to kind of capture it for being able to jack one side of the aircraft up. So ours is homemade, but if you're going to do a homemade job, you better trust your welding, you know. So you want to make sure that it's going to hold itself together. But if you want to see a sample of what one looks like, we've got one in the tool crib anyway. Jacking aircraft, there's jack stands that can be used for aircraft as well. Don't ask me how you get them on them, but if it's meant to be up for a long period of time, sometimes jack stands are recommended for holding aircraft up. This is the important part of using a jack, for at least a tripod jack anyway. That locking collar should follow the threaded shaft of the ram down as the jack is being raised. And again, if you're losing fluid as a result of a leak, it prevents you from collapsing the ram. Maintenance stands for aircraft. Yeah, they're hydraulically lifted in some cases. So again, make sure that they work correctly. And most often they have some type of tag on them to indicate the last service date on them. And never put anything to chance. If they have positioning feet that are on them, they obviously have to be positioned and wiggled in order to make contact with the ground when they're used. So sometimes there's dedicated stands that are used for aircraft. Ground support equipment, make sure it works correctly, make sure you know how to use it. If you don't know, ask somebody that does, get a checkout on it. And most of them, they have a calibration schedule for support anyway. And never remove or tamper or modify any of the safety devices that are on it. What you're trying to do is you're trying to prevent things like this from happening. And I don't know what the story was, but maybe they were attempting to replace the skid shoes on the gear. I don't know. A lot of Bell helicopters sport stellite-faced shoes that are on the landing gear, and occasionally the shoes have to be replaced. They're made of a wear-resistant material that they call stellite, but they don't use a jacking or a lifting device that can roll. And you know, this is obviously thousands of dollars worth of damage to the rotor blades. So again, don't know what the story was, but boy, it sure looked bad.
Where's the shoe?
The shoes are on the bottom of the skids.
And what do you say the material is called?
They're made of a material called stellite. The same material that they use sometimes for valves in aircraft, and it's a hardening material. It coats a piece of steel. Occasionally, the pad, rather than just have the landing gear leg or that are made out of aluminum wear, what they do is they have bolted to them. They have skid shoes. So this is another disaster. Don't know how that happened. But boy, that paint job's not going to look too good. Okay. Hydraulic support equipment, other than maybe just a simple rig for testing hoses. Cessna makes one. They're expensive, but they do have a purpose. If you have a hydraulic testing unit and you're checking for speed of retraction, this is a device that you can use in order to be able to do that. Not only will it check hydraulic hoses and rigid lines for leaks, but it affords you the opportunity to power things that would be necessary for checking for safe operation. So if you want to do a retraction test on the aircraft and you don't want to use the aircraft system for retraction, you can supply this unit and plumb it to the aircraft in order to supply for what the normal aircraft pump is doing for your retraction. but you can also use it for hose testing. I want you to remember, usually for hose proof pressure testing, minimum of about 30 seconds for Mohs hose testing, and usually it's 1.5 times normal system pressure for testing. They use what they call a pressure jack for hose testing. It's really just a modified hand pump in order to do it. But they also, again, they have an electric pump that supplies fluid through its own power pump that's regulated. So if we want to check retraction of gear, and not only that, we can regulate the amount of pressure. If you have to look at timing, so for example, if you're checking sequencing of doors and gears, the aircraft system is set at one particular pressure, so of course gear retraction and extension happens just like that. With this device, we can control the pressure so that if we have timing issues where we're trying to time gear and doors, it allows you to cut the pressure so that the speed is reduced, so for timing. So we can do that. This also has a temperature gauge as well. Sometimes if you know what the trend is in a hydraulic system, you can make some inferences on malfunction. If the temperature is higher than what it should be, it may indicate that maybe a pump is wearing itself out, or there might be excessive friction of some component. We use electricity too for troubleshooting purposes as well. Sometimes when you're drawing too much amperage in an electrical circuit for a landing gear, it sometimes indicates that the gear is out of rig. If there's a lot of required force in order to move an actuator to one position or another electrically, the motor is working really hard, so of course you'll draw quite a bit of amperage. In some cases, you'll cause a circuit breaker to trip. So, you can sometimes make some inferences if you know how much current is being drawn in electrical circuits. This is a self-contained hydraulic unit for testing purposes. And again, it's got mostly what the aircraft would have in it in order to be able to power it on the ground without use of anything this aircraft supplied. There's one important thing though to remember about these powered units that are used for testing. When you're using them for troubleshooting purposes, by their very nature, you are taking something out of the circuit that may be part of the flaw that was creating the problem. So, for example, these have their own integrated hydraulic pump in it. If the pump is malfunctioning in the aircraft, you've now bypassed the pump because you're using that device in order to power the aircraft. You all kind of see that, okay? So that's one of the big concerns when you're using troubleshooting equipment, is the equipment that you're using to troubleshoot, is it bypassing some of the normal, or bypassing a part of the problem, or part of the symptom that's causing the problem. So again, kind of something to think about anyway. There's some dedicated pieces of electric hydraulic power supply. This one came from an F-35, I think. This is from a Joint Strike Fighter. And anyway, it'll supply, first of all, it's powered either by a diesel motor or powered by an electric motor. But you can use it for ground testing purposes as well as servicing of the aircraft. So if you want to be able to check specific systems of the aircraft, you can do it. It's dedicated to one specific aircraft. There's universal testing units that are made for aircraft, but you have to use a little bit of care in operation of those devices because they allow for, in some cases, for application of pressure higher than what a particular aircraft might require. So again, you have to read very carefully what you're doing. One word of advice regarding anything that is powered by a gasoline engine that is powering like a hydraulic pump in one of these test stands. Always make sure that the clutch is disengaged before you start the unit. If you don't, immediately what you've got is a load on the hydraulic pump, and that can cause a pressure buildup that you didn't really anticipate. So if there's a clutch involved in connecting any type of gasoline or diesel engine involved in any of these test stands, make sure that the clutch is disengaged before you start it. And there's a lot of different portable test stands that are available. Some of them are used by the military for a lot of different purposes, sometimes even for purification of hydraulic fluid. It works kind of like dialysis of blood in the human body. But they're used for ground support. Some of them are electrically powered, some are gasoline engine, some are diesel engine powered. This is an old list, by the way, but in any event, there's a lot of them that are out there. Here's another list that kind of gives you some info on different types of test stands that are available for checking aircraft. We also have devices that are designed to provide pneumatic pressure. On some aircraft, they have pneumatic tanks that are used as part of an emergency system. In order to charge them with air, obviously you can't use directly shop air. That's usually regulated at 90 to 120 psi. So we have to have a dedicated compressor in order to be able to recharge flasks that require air under pressure for emergency use. And some aircraft still have that. Some of the old Cessna 300 series airplanes do have a flask aboard the aircraft that they use as part of a de-icing system. It's made obsolete today by more modern systems, but the old original 300 series Cessnas did use regulated air pressure from a tank in order to inflate pneumatic boots to break ice up. When they get low on pressure, you'll have to use something like this in order to recharge the tank. So many of the compressors are multi-stage and they're heavy. And that's not too much of a problem. With a ground power unit, they have the ability to provide for intercooling of air as it goes from one stage to the next of the compressor. But it's lubricated by its own source of oil, and they can afford the use of heat exchangers because, again, it's a ground powered unit to support the aircraft cylinder board for charging. And again, some rules of the road I think that are kind of important, and this applies also to pneumatic compressors. Always start with the clutch disengaged. If this thing is powered by a gasoline engine or a diesel engine, make sure that the clutch that couples the two is not engaged. Always engage the clutch at low idle speed afterwards. Put the compressor in the unload position before engaging the clutch. So whatever airflow is coming out of the fourth or fifth or whatever the last stage is, it's initially going overboard. Don't over-tighten the moisture relief valves. Shut down. Unload the compressor before the engine shut down. Allow the compressor to cool at fast idle before disengaging the clutch. And allow the engine to run with the compressor disengaged for 5 minutes. There's usually a cool-off period for a lot of these pneumatic components. And there's a reason. The lubricating oil that's inside of that compressor can coke and form into a hardened compound. Not necessarily sludge, but it will be like a hardened material that's very abrasive. So what you're trying to do is you're trying to prevent the coking of oil that will lead to contamination of the oil and maybe damage of the compressor by its abrasive nature. Even with gas turbine engines, you'll notice that they never shut down a gas turbine engine immediately after touchdown. They'll allow a certain period of idle time. And what you're trying to do is you're trying to control the oil temperature to a tolerable level prior to shutdown. And if you don't, varnish eventually builds up in the oil, and then that varnish eventually evolves into coking, which again is very damaging to the oil and ultimately to the aircraft engine. So you have to be careful. Control panel for it. Okay, so that's kind of what I have for you. It's now 5:30. Why don't you go out and have a break? I'll see you back here at 6 o'clock.